Okay, welcome everybody. Today we're doing a summary of the entire course. So we'll try to briefly summarize all of the topics and again repeat the most important topics we learned, learning goals, but also techniques. So that's basically the topics we had. We started with IMDb and I motivated the entire lecture through this web page IMDb, where you can look up information about specific movies, be it The Fifth Element or whatever movie you're interested in. I showed you a couple of screenshots. And then the question is, okay, what the heck? How do we model that information? How do we represent that information in a computer system? And then we ended up learning entity relationship modeling with all its components. We did that at length, looking at entity types, relationship types, attributes, and then these functionalities. Here it's only N-to-M, but it can be N-to-1 or one-to-one and so forth. So this is a correct entity relationship diagram. Here's again the overview of the modeling elements. I explained those, but then we also had inheritance, which is super useful, for instance, in hierarchies like user roles or something like that. They want to use inheritance. So the colors do not matter at all, but they just make the diagrams a bit nicer. Yeah, so this first question we had basically was answered with, modeling-wise, it's all entity relationship modeling and the relationship and the relational model. So first we draw the diagrams, that's the entity relationship model, and then we translate such a diagram into the relational model, which can then easily be translated into an actual database system to create an actual database schema. And the very important thing here is, as we're doing computer science and not programming or hacking or something like that, is this abstraction layer. So this is what we call physical data independence. So from the point of view of the relational model or the entity relationship diagram, we don't have to worry about whatsoever how to represent the data. So you don't worry about data structures, layouts, files and stuff like that. That's all handled automatically by the system. So we really abstract from the physical representation of the data. That's a big strong point of database systems to do that, because it allows us to change the physical representation later on. It also allows us to scale the system arbitrarily, and we don't have to make a decision. It's one server, it's 100 servers. It doesn't matter for the relational model, because it's completely decoupled from its physical representation. Yeah, and then so the question 2 was, how do we represent these links between different items so links between, like, you have actors, you have movies, actors play in movies and stuff like that. That's of course foreign key relationships that are modeled in the relational model. Yeah, and then we thought about the second week. We thought about, okay, how the heck do we query this stuff? Now we have it modeled in the relational model. How do we get certain information from that model? And that we do through the relational algebra. And the relational algebra comes with a couple of operators with Greek symbols or some weird symbols. And we learned how to use those. So we had the most important operators were those, of course, selection, projection, and then all these set operators, union, difference, Cartesian product or cross product, and rename. And then we looked, of course, a lot at joins. So in particular, the inner join or theta join. Theta join, as you learned, is basically reconstructing data along foreign key relationships. So you break the data into multiple relations, but at query time, you want to connect the data items again. So basically recreating, reconcatenating, if you want, data through foreign key relationships. So basically, this join is doing exactly that, along foreign key relationships. You can also execute joins along arbitrary theta conditions if you want, but typically it's done through foreign key relationships. Everything else is nice things to have, except grouping, of course. We looked at grouping a lot, grouping, group by, having, and so forth. But I will tell more about that when we look at SQL in a moment. So question 3 was answered, okay, how do we query this stuff with relational algebra? And then I made the argument, yeah, but it's a bit complex, it's hard to read, yeah, can't we hide it somewhere? Yeah? And that brought us to this fundamental theorem of software engineering. We can solve any problem by introducing an extra level of indirection, except for the problem of too many levels of indirections. Yeah? So this happens in all kinds of software architectures. You introduce yet another abstraction, yet another abstraction, yet another abstraction, and that's cool, that helps you to organize your software, but you lose performance every time, typically. It depends on how you introduce those layers, but there's a chance that you lose some sort of performance or an optimization opportunity also sometimes. Okay, so here, those are the main learning objectives we had in these first 2 weeks. I don't have to go, it's just for completeness for you to read through them, to make checks. Oh yeah, I know what that is. Oops. So if you go back and learn for the exam, you can do, oh yeah, check, check, check. What the heck is that? Yeah, and then you go back to the slides and learn it, right? That's the idea here. Yeah, make sure to understand grouping and co-grouping. Yeah, this relationship that co-grouping makes between grouping and join. So the group by operator is a weird operator that basically does 3 things at the same time. And there were slides where I explained co-grouping and what that has to do with joins. Make sure you understand that slide. And that's very important. Okay, then in week 3, we switched to what I called NSA. So I motivated that with a mass surveillance that's going on. Many countries are doing that, and the most famous case was the one of Edward Snowden, of course, who unveiled, starting in May 2013, a couple of documents, or not a couple, a ton of documents actually. And we investigated in particular the problems with metadata. Yeah? So the stuff, again, metadata is what the IMDb database contains. The IMDb database doesn't contain the actual movies, the MP4 or whatever video format you're using. It just contains metadata. Who played in the movie? Who directed the movie? How long is the movie? When was it produced? Stuff like that. That's metadata. Yeah, and this metadata sounds like, yeah, what can go wrong with metadata? Many things can go wrong. Yeah, and that is brilliantly explained in this book by Andreas Eschbach. And in the book, even he introduces SQL, explains SQL, but here I want to show you some slides again on the SQL we used in this lecture. So we used just a very fundamental, super basic statements you will always see. Yeah, and the most important statement is probably this one. So this is a read-only statement. And important for you is this conceptual order of reading it. So this again is here. So first you look at the relations. So from, those are the input tables. Then comes the where condition. The where condition may have join conditions, but it may also have conditions on individual tables. Then comes the grouping, then comes the having, and then comes the select. Yeah? And if you don't specify join conditions on tables mentioned here, those tables are combined through a cross product. Yeah? You say from R, S without specifying a join predicate between R and S, that will be a cross product in the result. So typically you want to specify a join condition. You can do that here in the where clause, or you can use this join on syntax we also learned about. Then comes the grouping. Again, make sure you understand grouping for the exam. So grouping is doing the partitioning on a specific key. Yeah? So if you write a key foo here, it will create horizontal partitions for each distinct value of foo that appears in the data set. That's very important to understand. Yeah, and then in the select, in an aggregation query, it will output one tuple per group it created previously. Yeah? And you can, in between, you can have a second condition, that's a having, not to be confused with where. Where is a condition on the individual tuples. Having is a condition on each group being created in the group by operation. Yeah? Once you created those groups, you can make a condition to the group saying, okay, I only want to have groups that have like more than 42 tuples. Yeah? Then you can phrase that in that having condition. That's totally fine. Yeah, and we had many examples for that. Yeah. Yeah, and then I promised you when showing these slides that I will show you these slides again. That's now, today's the time to show you those slides again, because it's so important and it leads to so dramatic costs in the industry. It's insane because people ignore that. So most common mistakes when dealing with SQL, again. So if you use SQL only in a CRUD style fashion, CRUD meaning create, read, update, delete, meaning, okay, you just store individual tuples, you retrieve individual tuples. It's basically a file system for tuples. Yeah? That's not the way to do it. SQL can do so much more, and you should really try to push down as much data functionality as possible down to the database system and make the database system do the heavy lifting. Because the true strengths of SQL remain unused if you do it like that. I mean, there are use cases where you do stuff like that, for very simple applications. Maybe it's just about tuples, that's fine. But as long as it goes into all kinds of analytics, grouping, joins, whatever, please delegate that to the database system. It will be faster. Yes, the second is, if you hear people say SQL and especially joins are slow, you want to use NoSQL, Hadoop or whatever, or implement myself, that's complete bullshit. It's not true. If SQL cannot be slow, SQL is a declarative language, and then it depends on the database system, then it depends on the query optimizer of the database system, then it depends on the physical design of that database system, then it depends on the hardware, it depends on so many things, but it's not a principal limitation. So if you have a problem with joins being too slow, don't switch systems. Just configure your database system correctly or switch to a different relational database system and you're good to go. So that's a mistake you shouldn't do. And the third is, that's unfortunately also available in textbooks. You see that sometimes, this claim that SQL cannot handle more structured data such as JSON, objects, graphs and stuff like that. That's all wrong. SQL can store everything. This limitation of SQL 92, it's gone. So the relational model was already extended in SQL 99 and 16 added JSON and stuff. You can put everything into SQL. That's all fine. If you want to do that, if you really should you put everything into SQL, into database? Depends. Large files, for instance. Large binary data streams maybe you don't want to put in your database system, maybe you put them on a file system, but for all kinds of medium-sized files or small files, you can put them in the database system. Okay, so how do we phrase more complex queries with SQL, obviously? That's what we learned. And then we also briefly talked about the ethical problems that arise from those kind of data collections and how do we deal with those. So civil disobedience, technical approaches, social approaches, and legal approaches. I gave you a couple of hints on what you could do in those situations. So here again, the main learning objectives. So again, for big data, this is buzzword, the problem, the most important takeaway is really this one, Äpfel und Birnen, apples and pears. So you add two completely seemingly unrelated pieces of information. We had that in that use case from the NSA book, information on what people eat, what they buy, what they consume, and the registration data from the city on who lives where. It sounds like completely innocent data, but if you join it, you can find out, oh, there's probably more people in that specific apartment than in the other. And like that, you can find hidden people, and that's what we learned. So that's the biggest problem with all this metadata, that you join data and it's impossible to predict the problems that may arise from joining possibly unrelated data items. That's the problem with big data. Joining stuff, so you have an idea, oh, what if I join this relation with that? And then, oh yeah, cool, now I got that information just by joining it. And that makes it very, very dangerous and also impossible to predict. I don't know how to predict this stuff. Haven't seen anything that allows me to say, okay, it's fine, you can join that. There is no privacy problem involved. That would be cool to have a technology that it can give you that guarantee. Here's your database. Jens, nothing can happen when you join this stuff. There's no privacy. Yeah, cool. Okay, that technology would be awesome. Maybe Turing Award. The Turing Award should be given to something like that if you invent that. Then that's a problem. So politically, joining data should be made as hard as possible. We looked at that also. Please remember this Corona warning app example, which is great. Yeah? This temporary keys that disallow for joining data, local computation on the smartphones rather than on a central server. Yeah? There's no central data collection on the server, but it's all kept on the smartphones. There's no key you can join on. These kind of things help a lot to make things safe. Yeah? And then we learned in Germany what happens if you don't do that. Yeah, the counter example, the bad example was this Luca app, which had a central server and which was then exploited by the authorities to track down criminals. Yeah? Okay, if you want to do that, it's okay, but it was not in the intent of the creators of that app, I suppose. Yeah? But once you have the data, it will be exploited. Yeah? So make sure it's not collected in central places in the first place. Okay, yeah, and then we eventually came to that question, okay, now what if the data gets bigger? Yeah, so how do we actually get from SQL to an efficient program? So that's all this magic a query optimizer and database will do for you. So we looked 2 weeks into query optimization. And yeah, I gave you this analogy. So basically different SQL engines or database systems, as they are called, have different capabilities. Yeah? So maybe a SQLite is more like a small boat which can sail only very slowly. MySQL is more like a motorboat. Postgres is more like an airplane. And modern database systems and research, but also research prototypes are like super crazy in their performance. Yeah? That's, I mean, sometimes hard to find a use case for these systems, but it's really insane what you can do with these systems. Yeah? Yeah, you won't need this stuff most of the time, so you will be happy with an airplane. Yeah? But sometimes even MySQL is enough, or SQLite or DuckDB is also great. Yeah? And then this is basically the pipeline that exists in those systems. So we start with some sort of canonical plan, so a translation of SQL into a relational algebra expression. Then we feed this into rule-based optimization. So we iteratively apply rules as long, so recall these rules have a match part, yeah, and then the transformation part. Yeah, so they check whether a certain pattern exists. For instance, oh, there's a cross product and a selection on top with a join predicate. Hey, this matches, I rewrite that to a join. Yeah, so that's the kind of things that happen here. And once this iteration terminates, well, you're entering cost-based optimization. In cost-based optimization, you enumerate plan alternatives and make estimates about the costs of those plans. Yeah, that's cost-based optimization, so costing, or you have cost models and those are estimates, estimating the execution costs of those plans. Yeah? So that's the job of the query optimizer to come up with these alternatives and choose the cheapest plan, or the plan with the lowest costs under the cost model. Yeah? And once you have that, you go into code generation, which means here that you either execute physical operators. This is also called interpretation, and this is done this is what we're doing in our Python notebooks. Or modern database systems, like our own system Mutable, for instance, generates code. Yeah? Generates binary code or some intermediate representation code, LLVM code. Other systems create LLVM bit code. Yeah? But basically something that's very similar to what a generic programming language compiler would do. Yeah? Like Clang generates at the end of the day binary code. Yeah? And that is very similar to what database systems do here. Yeah? And then this code is executed. Yeah? So basically here you execute a program that computes the results to your query. Yeah? This entire pipeline happens when you send a query to a database system. And it depends highly on the database system what the system does with such a query. Yeah? You can actually, in database core lecture, we learn that you can basically get rid of all of this. You don't need rule-based optimization. Who needs rule-based optimization? If you can start with cost-based optimization directly, yeah? but that's another story. So here's a couple of learning objectives we looked into. In particular, this logical versus physical operators. So the Greek letter versus its implementation. The sigma selection can be implemented through a scan or through an index access. This join symbol, this bow tie symbol. Huh? So I wore a bow tie when I had my PhD defense, of course, and not a tie, but a bow tie. I had to because I was doing my dissertation on joints. Yeah? So this symbol versus its implementations, yeah? Whether you have this can be translated into whatever, a hash join, or whatever, a sort merge join, or whatever. Many different techniques exist. So this is logical and this is physical. Okay. Oops. Right. Yeah, we also briefly looked at indexing. Yeah, for us, data, we don't call it data structure, we call it an index. Yeah, and we use different kinds of indexes than the ones in the data structures and algorithms lecture, because our indexes have to work well in the storage hierarchy in the computer architecture. And if you work with storage hierarchies, you briefly find out that, well, binary search trees are not so great, actually, in many situations. So here's again one of the images I used, that's a B-tree. And however the details look like in your B-tree implementation, the important thing is that you understand the principle. So the B-tree basically recursively partitions your domain. Yeah? If you index by a certain key, yeah, so the root node, what it does is it partitions the data space here into 3 different regions, distinct subdomains, so to say. Yeah? So the root node represents data from the entire domain, but the subtrees, yeah, this first subtree only represents data up to and excluding 43. For instance, yeah? Because that's the semantics here saying, okay, everything that's strictly smaller, 43 is to the left. Everything that's equal to 43 and strictly smaller, 91, goes to the middle. Yeah? That's this one, this interval, and everything else goes to the right. That's this interval. And that happens recursively. Yeah? So the next blue stuff here can be considered a complete B-tree at the end of the day. That's a complete B-tree. That's kind of the root node in that subtree, again partitioning the data space. Eventually you have these fancy subtrees that only consist of one leaf, yeah, that actually store key value mappings. Yeah? But again, they represent a certain interval from the key domain. Yeah? So that's a B-tree, and then there are all kinds of algorithms that make sure that the paths are always the same length, so B-trees are perfectly balanced and stuff. Different story, you can play thousands of tricks. It's also explained in the core lecture. But it's a super great index, no, it's super great data structure, what's the word? Am I allowed to say data structure here as database professor? Maybe, yes. So it's a super great data structure that works in the storage hierarchy. And it's a foundation for all kinds of indexing purposes in databases. Okay, yeah, so those are the learning objectives for cost-based optimization. So we looked at cost models. Yeah, again, keep in mind the cost model may model the costs for executing, yeah, in the sense of the time it takes to execute a plan. But your cost model may also be the energy being consumed or the network data being transferred or stuff like that. So that's very flexible, and you can just change the cost model and the optimizer will work. Yeah, this is this physical logical thing. I explained that already. Different dimensions of cost-based optimization. Okay, no, this is important. Okay, the join order we looked at, yeah, so which join order to take. So some join orders are cheaper than others, so we have to cost the different join orders. Decisions at the physical level, which physical operator to use. Yeah, like with the joins, is it a hash-based join or a sort-based join or whatever join? Should I use an index, yes or no? And again, recall, yeah, that's not so easy to decide. You may think that, oh yeah, well, if there's an index, I will choose the index. In a storage hierarchy, there are cases where choosing the index is a bad idea because it will ruin your performance. Yeah, that the reason is random I/O actually. So that's not so easy. Which resources to use for which subplan is another thing. Yeah? So how many threads to use, how much memory, stuff like that. The optimizer has to make a decision on that. Questions? Questions? No, good. So those were the learning objectives. We also talked about pipelining briefly. Yeah, so how do you organize the pipelines? You want to avoid materialization of intermediate results. It's an infinite story of tricks you can play. Yeah, many technical, interesting things happen in query optimization. And it's basically our daily business, yeah, in research, thinking about new ideas and how to organize these pipelines and stuff. Okay, all the other things I mentioned. Yeah, then we looked at what I call trading, banking, and ticket systems, motivated by these failures we had seen a couple of years back in banks, but every other month you see another failure of banks, which is kind of interesting that a company which has billions of money is not available to sustain such an important service like banking. I mean, that's a core business, having accounts where you can transfer money from one account to the other. I mean, that's not that difficult, right? How is it possible that these systems crash so frequently? Yeah? And the problem is not that they crash, but the problem is that they have a hard time recovering, and that took so long, a couple of days in some cases. Yeah, and then basically that was the first time when I introduced this term, database management system. So what is that database management system? And that's something you keep in mind. Yeah? So in particular, the features it comes with, yeah? All this great technology allowing you to make your life so much easier. Yeah? For instance, this extended relational model, or this super extensive SQL dialect, of course, depending on the system. You have automatic query optimization. As these query optimizers have become insane in what they can do in some cases. Yeah. Very high performance, massive support for physical design, so index structures and stuff. Support for modern hardware. Some of the systems, yeah, Postgres, for instance, not so much, but DuckDB supports that very well. Depends on the system. And then, of course, when it comes to dealing with these error situations, yeah, that early on, when people developed database systems, they wanted to support this stuff. They knew, okay, we have to be able to recover in a problematic situation. We have to be able to recover, to deal with situations where multiple people access the same database. Yeah? Recall the song by Joe Hellerstein presented, this crazy parody. Yeah? There's a transaction song. That's concurrency control is solving all of your concurrency problems for you. You don't have to work with logs and latches and stuff anymore. All of that is handled automatically, and this is super cool and avoids that application developers do errors, and that avoids that data gets corrupted, that avoids that the database gets stalled and doesn't react anymore and stuff like that. All of that is handled automatically. There are other features we didn't look at so much. One is automatic crash recovery. So database systems are able to recover from all kinds of error situations. That's also something for the core lecture. You can also use automatic consistency control, for instance, through triggers. I briefly mentioned that last week. It's a very powerful feature. You have things to configure access rights. You have dynamic views, stuff like that. So many things. Yeah, and the analogy for concurrency control was really this one, so keep that in mind. So the decision that was taken here was not to make the interface more complex, so that was the interface, yeah, and so this was this R-cluster, this Mercedes that had a problem in one of the tests. It was toppling over in this ELK test, and yeah, rather than making the interface more complex, they kept the interface. They had to keep the interface because no one can use this stuff, or few people can use it. So they kept the interface, but added some automatic stuff, which was meant to be, well, which was thought of to be a hack, actually, to be able to still sell the car. Yeah, but it was so cool that it became mandatory, at least in the EU, for all new cars. Yeah? So now in these problematic situations, all cars, the ESP will jump in and will make decisions to, when you brake, the car will automatically decide, oh no, I will lower the braking pressure on that front wheel, or I increase it and stuff like that. Yeah? So the wheels can can be steered individually by the computer. And this is really cool and helps you to not crash your car in problematic situations. Yeah, that's the same analogy here in concurrency control. Yeah? All is handled automatically. So how do we allow for concurrent modification of data without creating erroneous data? Yeah, concurrency control. And how do we do that in detail? There we looked at many things. Yeah? We looked at log-based concurrency control. Yeah? There is this other class of multi-versioning. That's, again, a core lecture topic. But this is also important to understand how this log-based stuff works. Yeah, and then there were many individual techniques, this is a huge puzzle, this concurrency control. Yeah? So I had to introduce many terms and concepts and ideas and how that works. Yeah? I mean, the major takeaways here are really, I think, let me start with this slide. Yeah? So try to avoid, there's again a confusion of these terms, conflict serializable versus serializable as an isolation level. And when we learned about conflict serializable, we basically learned, okay, it's conflict serializable if its execution order is equivalent to one serializable schedule. Yeah? However, you're still not safe because if your schedule contains transactions that did not commit, yeah, those transactions may have done changes to your database system. Yeah? But ACID forbids that. A transaction that does not commit must not change the database system. So this is not enough. If you only have committing transactions, conflict serializable is fine in many regards, but you have to do more. Yeah? Yeah, so once we had that as a theoretical concept, we learned, oh, there are so many things, and also these predicate logs and stuff and blah, and deadlocks. Yeah? So there are many things you have to do, but all of these problems can be solved. So don't confuse conflict serializable and serializable. That's very important. And yeah, we looked in particular at, so we learned that most database systems guarantee atomicity and isolation. Yeah, so this A and I from ACID for transactions are guaranteed. Modulo Oracle does not guarantee perfect isolation. I showed that example where they ignore write skew. But all other systems, or most other systems, do that. But you have to be careful with the isolation levels. So when you install a database system, it typically has an isolation level of read committed rather than serializable. Yeah? So if you use a database system, first thing you do is change the isolation level to serializable. Okay. Yeah, I think I don't want to go through these things. Right. Okay. Yeah. Then I think that's all I want to say about that. Let me also think about this Mensa analogy I mentioned several times. Yeah. So so how do you solve isolation issues? Yeah. If you think, I mean, you go to Mensa, you grab a chair, you want to make sure that no one else sits on the chair. Yeah. I mean, you can avoid these kind of problems that you get in conflict with other students in Mensa by just making sure that you are the only one to use the Mensa at any given time. There's only one student in Mensa at any given time. If the student is done eating his or her lunch, okay, then the next student may enter. Okay, this is a completely stupid way of using Mensa, of course. That's not very effective. So you allow for more students to eat in Mensa concurrently. But you have to make sure that they don't have conflicts. They don't sit on the same chair. Yeah? They don't bump into each other. They don't run over each other and stuff like that. And what the database system provides you with is a concept we call isolation. Isolation meaning from the point of view of each individual student, it looks like as if the student is alone in the Mensa. So again, you have these glasses here, this virtual reality glasses on. You go to Mensa and there's just no one sitting there. No one is there. Yeah? And no matter what you do, no matter how you move, everything is fine. It looks as if you were using the Mensa alone. It's just you in Mensa. Whereas in reality, it's crowded with people. Yeah? And you also have noise cancelling headphones to not hear the talking from other people. And that's what the database system gives you for free. I think this analogy captures it very well. Okay, yeah, and then again we turn back to IMDb, so IMDb part 3, and because here we looked at the data modeling stuff, but we didn't look at, okay, now how do we get the data out to the user? How do we provide the user with the information? How actually does the IMDb web page get the data out of the database to the web browser? Yeah? And that is what the web application is doing. And there I showed you this layered architecture, this extreme version of a layered architecture that you can create. So, I mean, there's hardware, there's an operating file system, sure. There's a database system sitting on top of the file system. But then, hey, there's another layer of another indirection layer. So now all of a sudden we don't send SQL as an application developer. We don't write SQL statements anymore. So if you use a backend framework like Django, Django ships with Django ORM its own query language called query sets. So you only write query sets, and the query sets get magically translated into SQL. Yeah? So actually, when
developing with this stuff in the past year, we found out that there are a couple of issues in this ORM, and that's now a bachelor thesis. So, of a bachelor student working on that, and you already found a couple of interesting things that we can fix. Yeah? So it's not perfect, this thing, yeah? But conceptually, you only write your application code in Python in this specific case, if it's Django, yeah, containing those query sets. So your application runs in this framework, and part of that framework is that ORM which translates the query sets to the database system. Yeah? And then the database system executes SQL, returns tuples. The tuples get translated back by the ORM to objects in this, so objects of models in the ORM. We had a couple of slides on that. So all of this database stuff is hidden. Actually, from the point of view of your backend application, you don't have to know that there's a SQL database sitting underneath. You don't care. It's abstracted away. So you could, in theory, also run Django on whatever, a non-relational database system or on a file system, if you believe that's a good idea. Yeah. So all of that is hidden. Yeah? So you don't see that from the point of view of the backend application. Yeah, and then there's a UI application. You could also decouple from your backend application. That's a good way of doing that. A good practice, common practice, and then there's UI, and then there's user. So you have this huge stack, these layers, different architectural layers, which if you don't have too many of those, make your life easier, yeah, because you separate the concerns, which makes software development so much easier. Yeah. In particular, you can also replace layers, and that's a very cool thing. You could, for instance, kick out. If you used we did that in the project, for instance. Initially, we used SQLite. You shouldn't SQLite for production system in Django, so we switched to Postgres eventually. If eventually we feel like Postgres is not good enough, we switch to a different system. Yeah, that's all fine. You typically don't have to change anything on the layers on top. Yeah? They're completely agnostic about that database system. Yeah? And that's a very important thing. Okay. Yeah, we also talked about security problems with databases, the most prominent being SQL injection. And again, that's one of the most important takeaways from this course is be really careful about these things. If you see that in practice, fix it immediately. If you see that in code you're responsible with, or even you do peer programming and see a colleague did something like that, give that colleague a hint, hey, maybe a SQL injection would be possible with your code, maybe you want to fix that, because it's super widespread. Yeah? And many data leaks are due to this problem. And the problem is always you have a situation where you have a SQL statement as a string, and in your code you do a string concatenation. Then you're in trouble. That's it already. That's already the bug. Yeah, that's the problem. You shouldn't do that. And the problem occurs because you concatenate the strings, then you have this huge string, and you give that string to the database system and leave it up to the database system to interpret that string.
So the database system will find out, okay, that's part of the statement, and that is a constant, and so forth and so forth. That's the problem already. Yeah? You must only use SQL. You should only use it like that, where you have a placeholder. Yeah? So we have that in our Python notebooks, where you when you phrase a query that has a parameter, you write it like this. Yeah? In this syntax. It's a colon and then the variable name. Yeah? So the blue part is a statement, this orange part is a placeholder, and then when you send it to the database system, you send it through a command that has two parameters. One is this query, and the one should actually be blue here, right? Yeah, that should be blue, and the other is the parameters. Yeah? And then it's crystal clear that the database system will execute it such that the semantics of the query are not changed. Whatever you insert here, yeah, and in this case it's this wild username, this will be considered the constant to compare with. So where name equals single colon or tra-la-la-la-la. So it's really used as a in comparisons here. So this query would only return those users that have that weird name. Whereas in this situation here, when you do the string concatenation, this query would return everything because you changed the semantics of the query. Yeah, so that's really a fundamental rule in all. So I'm not a security expert, but I learned from one of my students in that project. So there are tons of injection attacks, not only SQL, but in other variants, in other situations in software development. And they all start with something like that, where you concatenate something, and then you leave the interpretation up to some system, rather than enforcing, hey, no, that's a statement, and that is a variable. Yeah? It's super important. If you see that, you feel like, what can go wrong? Huh? But it's this little problem has dramatic consequences. And of course, I showed you this super famous joke, of course, little Bobby tables. So in Germany, I think it's not a problem because we keep these records on paper. So we are safe against SQL injection. Okay. So then we entered data journalism, and I motivated that with the idea that journalists more and more have been using data in their news articles. No, it's not just a static snapshot like in a printed newspaper, as journalism is happening more and more in the web, of course. You can basically enrich your web pages with data. And that was one of the examples I showed where you could show the voting results, the election results for any of those counties. Another example was investigative journalism. Maybe that's the name. Yeah, so people really get access to data through SQL injection, most of the cases, and then get information about like tax evasion strategies and stuff like that. So the Panama Papers, or this was the Paradise Papers, was an example for that. And then they try to organize that data in a graphical way. So I had this example like an inspector investigating a murder, and then basically what you always see in these movies is there's this blackboard or whiteboard where they put like a piece of information here, a piece of information there, a photo of a suspect, stuff like that, and they connect it through threads, and that's basically a graph. And the same graph was done in this project, but not on a physical whiteboard, but through a graph database. Yeah, we thought about two things. Okay, now there's the graph. How do I represent the graph? The first thing we learned is, in terms of data modeling, entity relationship modeling is just fine. So we had multiple approaches to model a graph. It's completely, there's no problem. It's actually perfect to model a graph. However, when it comes to querying, SQL is not so great. Yes, we have this recursive, and it's not completely unreadable, but very unreadable for these queries. So you want to have something else, and this something else language could be something like Cypher. Cypher is one of these
graph languages that was proposed. However, what you want to have is actually an integration at the end of the day. So, what is this doing? You want to integrate SQL with a graph language. Yeah? So basically, be able to have a combined query querying in SQL style and graphical style. And that makes a lot of sense, in particular, if you don't go for specialized database systems. So you don't have a separate relational database system for your non-graphical stuff and a graphical database system, a graph-oriented database system just for the graph stuff, because that leads to all kinds of problems. Yeah, we went through that in the lecture here. Told you about the maintenance. Yeah, you have to have 2 database administrators. How do you make sure that the data is consistent? What do you do with queries that touch both of the data, the relational data, the graphical? It's insane. It doesn't make any sense. Yeah? So always make sure, if possible, to consolidate on a single system. And then there are always people that make claims, yeah, no, the relational database system can't do that. It's too slow, whatever. That may be true for certain products for a certain period of time. But at the end of the day, whenever there's a new use case for data management, the stuff will be integrated into the major flagship database systems, and then you will be able to do those things you want to do in those systems. And that's the way to go. So try to use a system that supports both of these things. For Postgres, there's this Postgres AGE project that does exactly that. Integrates Cypher with SQL, and then you have a single consolidated system. Yeah, so that's basically the major takeaway here. Yeah, to model, you use entity relationship modeling and relational model, but to query, you want to have Cypher or something similar, and that preferably fully integrated into a relational database system. Yeah, those are the learning objectives again. Yeah, again, that's very important. Yeah, there's no need to use a different modeling language. If it's, I mean, there's this question you may have in a project, okay, I could be using UML, right? If it's just about the static data, about the data model, the relationship of the data, entity relationship modeling is fine. UML, of course, has other sub-languages to allowing you to model like use cases and behavior and stuff. Yeah, okay, you don't have that with entity relationship. But just for the database part, I don't see a need to use UML, really. Okay, this, we also talked about basic safety measures, if I remember correctly. So you want to hide the database in a web application. Yeah, from the point of view of a user of a web application, the user should never be able to see the database. So which database are you using, what is the connection, and stuff like that. That's all hidden in the application server, stuff like that. Okay. Yeah, and then we made this lecture last week where I showed you a little bit, this divide between data in academia and data in reality. Yeah? How is data being handled? What you should do, what your professor teaches you versus what people really do. Yeah, and we went through these different concepts, and I gave you some ideas on how this is done. In reality, in particular, you will see that you have all kinds of wild schemas no one really understands. It's schemas with hundreds and thousands of tables. Yeah. SAP systems, there's a rumor that they have 10,000s of tables, and they're shipped with no matter which application you pick. And I mean, who is going to understand this stuff? Yeah. And one reason for that many tables is that these systems got developed over time, and people kept adding, oh yeah, I need this functionality, I just add another column, I add another table, probably without understanding what's already available. And then you end up in situations where we have functionality modeled multiple times, yeah? Or even conflicting models and confusion, which leads to insane costs and super insane problems in application development. Yeah? So I'm also learning that in the web application I've been developing in the past year. If you have to do one thing you really have to make sure about is you keep your data model clean at all times. Never make any compromise. Once you start making compromises, it's over. Yeah, there shouldn't be any compromise. And if you feel like, oh, that's a compromise, that's a weird thing, remove it immediately. No matter what the costs are in application development, remove it, get rid of it. Yeah?
That's the only way to avoid this problem that you have a shitty, messed up data model. Yeah? And organization, in terms of organizing that, what you could do is make sure that only very few people are allowed to change the data model. Experts, database experts should be allowed to change the data model. And if an application developer wants to add another column, wants to add another table, he or she should come to that person and convince the person to, hey, I really need that. Yeah, please add the column. And then that database person should say, no, here, you can do it like this and that. Do we really need that? Why is that a use case? Can't we represent it in different ways? It's super important. Yeah? In any project, I would always, we do it in this project like that, but I will I really learned it how to do it now, and keep your data model clean makes a huge difference and saves a ton of costs, actually. Yeah, and then I showed you these fancy slides about this buzzword confusion. That's really important. It sounds like, it's Professor Dich made a nice joke. Who cares about that? I'm sorry. Here's bad news for you. You will see that all over the place in practice. Yeah, and hard to see projects where that is not a problem. Yeah? So people have different translations. In particular for buzzwords, big data may mean a ton of things. And if you try to use that in a technical conversation, you're in trouble. You won't solve the problem. So don't use buzzwords in technical conversations. Try to use unambiguous terms, like the terms we learned about in this lecture. And if you are in a conversation where there's a term in the room that is ambiguous, make sure you clarify. You lift the fog. Get rid of that ambiguity. That's very, very important. You feel like, oh, he's using the term differently. He means a different thing. Then say, stop. Okay, maybe you mean something like different. Maybe we use a different label for that. Those are all labels. And make sure that the labels don't conflict. That really hypercharges and speeds up your technical conversation. And then the other thing I told you about is this stuff, these confusion of dimensions, also very widespread in development in industry, but also at university. You, as a computer scientist, or whatever you study here, you should always solve problems in dimension 2. Technical principles and patterns, concepts, best practices, but not along the lines of specific software platforms. You're not solving a problem in Postgres. You're solving something on the SQL level, on the relational model level, on the entity relationship model. That's all fine. On some abstract ORM model, I'm totally okay with that, but not on a specific product. Then you end up in developer hell. It's really a problem. I mean, I don't know, whatever. Don't get me started on that one. So those were the learning objectives. So I gave you some ideas on situations where you have to reverse engineer a database. I gave you ideas on best engineering practices and specific these deployment environments, staging, production, test server environment. Look at that. That's super, super useful in a real project. And the linguistic confusion, of course. So what's next? So we will offer a pro seminar that's called, in the next winter term, that's called Techniques for Building Scalable and Robust Web Applications, inspired by IMDb Part 3, of course. So basically, we continue where we ended that lecture. So the question is really how to deploy, scale, test, and performance monitor web application. There are great tools out there allowing you to understand whether your web application is up and running. Don't leave it up to your email account. Oh yeah, by the way, your web application is down. You have to monitor this stuff. So we will look at state-of-the-art techniques and tools, and that's organized as a block seminar, meaning you work on that throughout the semester, but towards the end of the semester, like probably mid-February, there will be a couple of days where everyone gives presentations and a hands-on demo. So basically, we look at different techniques. It could be Docker, it could even be GitLab, it could be Kubernetes, it could be whatever. And you should
then give a talk about that, but also a hands-on demo. Yeah? Not just, you execute this command and this happens, but really where we see, oh yeah, you really understand what you're doing. And the major focus in your presentations will be given to how much you explain techniques along dimension 2. So technical principles and patterns and concepts. What I mean by that is really, if you look at Git, for instance, Git is awesome, it's great, but the terminology of the commands is not so great. It's really confusing. Yeah? If you say, what do you pull, Git pull, what do you actually pull when you pull? Is it, it's a fetch and the merge on the current branch, but what is fetch doing and what is merge doing if it's fast forward? Yeah, so it's really unfortunate, the terminology. And so if your topic would be Git, yeah, I would ask you to give a presentation where you explain Git along the terms learned in this class or in other computer science classes, conceptual terms, not the terminology used in that specific tool. Yeah? So if you introduce Git pull, you would have, you should invent a different term. Okay, now I call this Git get log entries or stuff like that. Yeah? If you don't come up with a term, you can still have an explanation on the side, and then we come up with an explanation during the presentation or before. So what do we learn in this class? What will you learn? So you will learn how to give a presentation. That's a major feature of these pro seminars. However, how I will do it, I will give you one class, like 90 minutes, with very strong guidelines how to get a good presentation effectively. So I have quite some experience with presentations, and I will give you, we did that many times in seminars where I really explain briefly how do you effectively organize presentation, how do you get going, what do you put on your slides, stuff like that. So that's I think in the middle of the semester or something like that, we will do that. Yeah, then how to conceptualize, you will really train your muscle on that. Yeah, get away from this gibberish, this developer gibberish, and drag stuff towards dimension 2, the concepts. And of course, you will learn a lot about technical stuff about web applications. Yeah? So you won't have the time to try out all of these techniques. But one thing that's very important here, and that's the biggest, one of the biggest obstacles in developing web applications that I experienced was really understanding, oh, there is a tool already that does exactly what I'm looking for. Yeah, sometimes very hard to find those tools. Yeah, for instance, this containerization. Okay, I was aware there's Docker or something like that. Yeah, but sometimes it's you don't know. There is this perfect tool out there for you. And I mean, you don't have to learn all the details about the tool, but when you're in a situation, you have to know, oh yeah, there's a tool for that. I can assign a couple of people on that tool just doing that. Yeah, that will fix my problem. Yeah, that's so valuable information, and you will learn these kind of things in this seminar. Okay. Yeah, we also run a core lecture every other year, which means the other year, not this year, because we did it last winter term. So not in this winter term, but in winter 24-25, there will be another iteration. And there we look at stuff like, so yeah, how does an aircraft turbine work in detail? How do we fly at 100 times the speed of light? So who cares about physics? Come on. Are there wormholes, and how do we fly through them? How can we guarantee the safety of the passengers even in the event of a crash? How do we build a distributed database system the size of a planet, the galaxy, or the universe? Yeah? The techniques are there for doing these kind of things. Yeah? So if you want to do that, that's kind of, I mean, that's a little bit, goes a little bit away from reality. Yes? So this class is really performance oriented for crazy cases. Yeah, but also, yeah, these applications exist. They have these performance problems, and in this class you learn how to solve those. Yeah? Yeah, then, other than that, of course, we offer thesis, bachelor and master thesis if you're interested. I'm not sure, what should I mean, topic-wise, it has a lot to do with the stuff we do in class, of course. Yeah? So currently we do a lot of stuff with web applications and Django stuff. If you're interested in that, I think I have at least 1, 2, 3, 4 students working on Django stuff currently. Others work more on query optimization, often as part of our database system Mutable. That's more like C++ development, often. Others do standalone
prototypes. We have one master student who just is working on indexing. He's currently doing prototypes in C++ on indexing. Yeah, so we have all kinds of topics. So if you're interested, just approach me and then we will find a topic. So I don't have a carved in text, carved in stone list of topics, yeah, because these topics appear here and there magically. Yeah, but if you're interested in a thesis, approach me and then typically ask, okay, what are the topics you're most interested in, and then we try to find a topic. Yeah, that's how it works in my group. Okay. Yeah, next summer we will probably be running this lecture again, and we are already looking for tutors. So if you achieve at least a 1.7 in the exam of next week, have a talent for explaining, would like to join our team, then apply directly to me, just send me an email. Content-wise, the lecture won't differ probably. So like this year's lecture, the content differed by 1 week. Yeah? So we introduced Django, we reduced data journalism from 2 weeks to 1 week and introduced Django. Not sure what happens in winter. Maybe I run into another great product or idea. I feel like, oh yeah, let's drop relational algebra. Who cares, right? Not sure. I guarantee for nothing. SQL is probably going to stay. And entity relation. So the least things to drop. Yeah, that's an interesting question. So the least things to drop are the entity relationship model. Yeah, I could exchange everything else, but ER I would never change. Yeah. Then it's SQL. Query optimization is super important. The graphical stuff, yeah, it's a niche. Come on, let's face it. Transactions, oh yeah, that's hard to know. It's 2 weeks is tough, right? It could actually be 3 weeks. Yeah. And what else did we have? Where's the overview? I forgot what I told you. Where's the overview? Let's go here. Database to the web. Now this is too cool actually. Query optimization, NSA, privacy stuff. Yeah, no. SQL injection. Oh, no, you don't want to leave that away. Yeah. So probably I would kick out relational algebra actually, but then it's hard to do query optimization. I think I would kick out rule-based query optimization because that's something you can get rid of. Yeah? And once you do that, you still have a problem because for cost-based optimization, you create those plans, and yeah, it's hard to get rid of relational algebra. Maybe I can tune it down to only explain it as part of query optimization. That's what I would do. Anyway, yeah, but my message is probably not so much. Yeah? I'm not going to change it that much. Yeah? So if you're interested, let me know. And tasks are giving a tutorial, participation in weekly team meetings, co-conception of exercises. Yeah, we have a huge pool of exercises. So it's always like we reuse stuff from previous years, change it slightly, but also like at least one exercise is completely new. That's how we do it. Yeah, you should correct exercises and exams. And the mode is, as this year, they're group hand-ins, of course. So that lowers your workload anyhow, right? Yeah, with that, I hope you enjoyed it and learned a lot that will help you in your professional career. If you end up working with databases somehow, feel free to drop me a line. Tell me about your horror stories, your positive experience, or just challenge me and say, no, what you explained is complete bullshit. Yeah? Or here, there's something you should add. Yeah? You should get rid of this topic, and really, this is so much more important. Please add it to your lecture. I really love to have this kind of feedback. With that, thanks a lot, and good luck. Thanks.